Hello, my project is a Sudoku solver in Python that uses a brute force backtracking algorithm. The goal was to create a program that can automatically solve any 9x9 Sudoku puzzle from a TXT file. Sudoku is a great example of a constraint satisfaction problem where each cell must follow specific rules so that every row, column, and 3x3 box contains all numbers from 1 to 9. I built the project in Visual Studio Code, as you can see. The solver first reads the puzzle using the readGrid function, which is right here, where zeros represent empty cells. Then, the printGrid function displays the grid in a clear and readable layout. The core of the program is the backtracking algorithm. The findEmpty function looks for the next empty cell, and valid function checks if a number can go there without breaking Sudoku rules. Then the main solve function then tries numbers from 1 to 9 if a number fits, it continues. If not, it backtracks and tries another option. This continues until the entire grid is complete. The program also measures steps, recursive calls, backtracks, and execution time, as you can see here. When it runs, it prints both the initial and solved grids along with these statistics. For example, an easy puzzle solves in less than a second with only a few hundred steps. Right here, this is an easy grid. I tested it with different puzzles. Easy, here, hard, medium, and hard, to make sure it works for all difficulty levels. In every case, it found a full correct solution. I'm now going to try again with a hard level. So I'll input hard.txt, and as you can see, it's a harder level with less numbers in the original grid, and it shows how much time it took. It shows the solved grid, and it shows backtracks, recursive calls, and the total steps, of course. After this, I compared this brute force solver with a theoretical A-star approach. While A-star uses heuristic and explores smarter paths, it needs much more memory and it is harder to implement. For Sudoku, the backtracking approach is simpler, faster, and perfectly effective for standard puzzles. In summary, this project shows how AI search concepts like recursion and constraint satisfaction can be applied to real problems using a clean and efficient Python implementation.
Hello and welcome to my part of the project presentation. In this section, I will present the PDDL domain and problem implementation for our autonomous rover mission and demonstrate how it was tested using the planning domain online editor. So let's start by the domain file. The domain describes a lunar exploration scenario involving a lander, a rover, and several waypoints. At the top, we define the object type, which include the rover, the lander, and the waypoint that the rover can visit. Next, we have the constants, like the photo scan, which is important for saving data and collecting scientific data. Next, we have the predicates, which represent the state of the environment, for example, whether the rover is deployed, its current position, whether a sample has been collected, or if data has been transmitted to the lander. Below that, we define the actions that the rover can perform. These include deploy to activate the rover from the lander, drive to navigate between waypoints, and snaps or scan to collect scientific data, and unplug photo to send the collected data back to the lander. Each action has specific precondition and effect, ensuring that the rover behaves logically. For example, it can only move if it's deployed, and it can only transmit data after collecting it. So now let's explain the problem file. Here I define the object, one rover, one lander, and several waypoints. The initial state describes the starting condition. The rover is located at the lander site and it has not yet collected any sample of data and no images or scans have been transmitted. And then we have the goal state defined that the mission must achieve. The rover must have taken an image and a scan collected and deposited a sample and transmitted all the gathered data back to the lander. So now let's test the model. So for that we can press the solver button. I use the built-in Llama First Planner, which is part of the fast download framework. When I run the solver, it passes the domain and the problem builds the causal graph of all possible states and begins the search for an optimal sequence of action. So let's take the first one. The generated plan starts with deploying the rover from the lander, moving through multiple waypoints, taking an image and a scan, and uploading the photo back to the lander. This confirms that the domain and problem are complete, logically consistent, and functionally correct. The planner could understand all the preconditions and effects and produce a realistic autonomous exploration plan with all the states. In conclusion, this PDDL implementation model a fully autonomous lunar rover mission. The successful plan generation demonstrates that the domain and problem were well structured, the predicates and action were clearly defined, and the planner could execute a complete mission from start to finish. This part of the project shows the power of automatic planning for decision making in autonomous robotic system. So thank you for listening to this demonstration and watching my demonstration.